Hey everyone, welcome back to my Calculus 1 series. In today's lesson, we're going to be going over the substitution rule for integrals. So in previous videos, we've discussed ways to evaluate these simple integrals by memorizing or kind of working through that chart that I gave you. I'm going to link a card up to it, go back and review if you don't know. But what if we have more complex integrals? Like, not all functions that we can integrate fit in that chart. That chart was very limited. What if we, for example, have a function like this, right? There is nothing on the chart that tells us how we can differentiate something like this, for example. So in today's lesson, we're going to be going over another way as to how we can kind of solve these integrals by breaking it down into those smaller integrals that we know. And that's basically what the substitution rule is about. We're going to try and get rid of functions through some substitution, so that basically we can get a I'm going to call it like a primary function, a function that was in that table that we kind of know how to integrate. So here's kind of the formal definition of what the substitution rule is. And essentially, if we're going to label this variable u with some function called g of x, right? And this function is differentiable, whose range is kind of on this interval I, and then f is continuous on that interval. And you'll see why we do that. It's because right here, the function g of x, its range is the input into the function f, so we need f to be continuous on that interval. Now here is the substitution rule. Essentially, if we have a function right here composed of another function, and then we see the inner function's derivative also kind of on the outside of everything, then this is a perfect candidate for substitution rule. In general, if we see that a function contains this inner function, and then it contains a derivative, the derivative of that function outside somewhere, that's a good indicator to start applying the substitution rule, or at least give it a look. And so if this condition is met, where we have this composition of functions, and then on the outside we have the derivative of the inner function, well, then we can simply say that this is equivalent to f of u du. Now let's not forget that u is up here. This is what u is. So u is that inner function. Now let's go back to the example that we have shown, right? We've started off with this example right here, and you're probably wondering as to how we can solve it. So I'm going to choose to solve this problem right now. So here we are. We see that this right here, well, actually, let's first identify all the functions, right? F of x in this case, the outermost function, is going to be the square root of x. The inner function, this one right here, is going to be g of x, and that's going to equal to 1 plus x squared. And lastly, g prime of x is right here. And we could see if we differentiate this, we're just going to drop the power, and then 1 is going to be a 0. So it indeed will be 2x. So here are all the three functions. And if we just want to go based off the definition of what this substitution rule is, well, then we can say that this integral right here is going to be equal to the integral of f. So f of u in this case, and again, u is g of x, as we see from the definition, so it's going to equal to this. And now if we just substitute our stuff in, right? So f is going to be the square root of x. However, the input is u, and we're just going to keep the u. So there it is. Now this is the integral that we have to solve, and we kind of see how this is broken the integral down in a sense. Now we're left with just this single primary function, which is the square root of u, and it's pretty easy to integrate that. So I'm going to go ahead and do that right now. So there we go. We have integrated this function with respect to u. However, the original question was not in terms of u, it was in terms of x. So we kind of need to go back, and we can kind of resubstitute. We know that u is equal to this right here, so we just say that we're just going to substitute it back in. Basically something like this. This is our answer right here, and if you want, you can go ahead and use chain rule and kind of solve, and you will get right back to this equation right here. You will get right back there. So you can check that out on your own time, but as of now, I'm just going to show you another method, the method that I prefer to use to solve these integrals. So again, let's say we have this function. This is the method that I like to use, dx. So what I do is I don't like to find these three functions and kind of just memorize what this is here. I'm not a big fan of that. So what I like to do is I like to just evaluate this inner function right here. So I say that u is equal to, by the way, you can use any variable. Most people just end up using u. So that's why I use it too. So I say that u is equal to this inner function right here. And now what can I substitute in for? I know that because I'm going to be substituting u in, this dx, it's not going to be dx anymore, it's going to be du, because the function will have, the integral will have the variable u in it. So we're going to need to differentiate with, or sorry, integrate with respect to u. So I need to change this dx right here to a du. How can I do that? Well, I know that if I take the derivative of this side, I will be left with this, with 2x. And now I can see that du is up, or sorry, yeah, du is up here, and I'm going to need to isolate for that. But I'm not going to isolate for it because I need to kind of cancel, I need to substitute something in for dx. So what I'm going to do is I'm actually going to isolate for dx. And if I plug whatever I have for dx into that, into here, then I'll be left with du. You'll see what I mean. So I'm going to right now isolate for dx. I'm basically going to cross multiply this upwards. So I'm going to be left with du over 2x is equal to dx. And now we have a formula for what dx is. It's right here, and I'm going to substitute that in. So I'm going to end up getting the integral of 2x times the square root of u. We said that the inner function was u. And now dx is equal to du over 2x. And you can see kind of how we've, in a sense, we've like kind of injected du into this, but this is the way that I personally like to do it. And now we can easily see that these two will cross out, and we'll be left with the integral of the square root of u du, and we're kind of right back at this step right here. Personally, to me, this seems a little more like the way I like to do it. So yeah, again, this is the method that I like to use. I'm just going to show you both methods, and you pick whichever one you want to use. For another example, here it is. Again, using my method, all we got to do is evaluate or find this inner function. So we say u is equal to x to the 4 plus 2. And now from here, we need to get rid of this dx. So we kind of need to find out a formula for dx. So we can do that by saying du over dx is equal to 4x cubed plus 0 would be actually. So it's just 4x cubed. And now we can go on to solve for dx, and dx is going to equal to du over 4x cubed is equals to dx. Now we can go ahead and substitute whatever we know into this integral. So we're left with the integral of x cubed cos of u, and then instead of dx, we're going to put du over 4x cubed. Now we can see that these x cubes cross, and we're going to be left with the integral of 1/4 cos of u du. Now I prefer this method because it's pretty easy to see what constants you're going to have. So in this case, because we injected this kind of du into it, we were forced to add this constant of 1/4, and here it is. So now it's pretty easy to see for me. At least this is, again, the method that I prefer, so this is what I like to do. And now we can just go ahead and solve this integral. So we're just going to use the integral properties, bring out the constant, and we're going to be left with cos of u du. And now we can see through this kind of manipulation by letting a function equal to u and then working with its derivative, once again we have simplified it to this, in a sense, like a primary function, one that we know how to find the integral of. So this is just going to be 1/4 times the sine of u plus c. And then u right here is just it's the definition for u is up here, so we can just plug it back in. So we can say that this is sine of x4 plus 2 plus c. And there we go. We have found the derivative, or sorry, the integral of this big function right here. Again, you can use the other method right here. You can use the definition of it. I just prefer not to. I prefer to kind of just work through the steps of things. It's a little more visual to me, and I can kind of cross-reference my work after. So here is the last integral that we're going to be showing as an example. And the reason I show this one is because a lot of people kind of get stumped as to how we can solve this, because they immediately jump, oh, like there's no outer function or whatever, but in reality there is. And I will show you why. So here, right there, that's the inner function. So we're going to say u is equal to 2x plus 1. Now if we take the du over dx to find a formula for dx, this is just going to equal to 2. And then we can see that dx is going to equal to du over 2. And now we could see what I meant by there is that outer function. That outer function is simply just a constant function. It just doesn't have an x value, right? Before we used to have, it was pretty evident that, oh, here's the outer function, And then in this example, like here it was 2, but if we see that the derivative of this inner function is just going to be a constant, that substitution rule will 100% work. So again, here we are, we have dx, we have what u is, time to just substitute this stuff in. So we're going to be left with the square root of u, and then dx is going to be du over 2. And again, it's nice because we get to see what our constant is, so it's going to be a half. So this is going to be the integral of 1/2 times the square root of u du. So there it is. And now we can go on to simply solve this. Again, I'm going to bring out the constant, keep the square root du, and we've already solved the square root. So all we have to do is just, it's u to the power of a half. So we add 1, which is going to be 3 over 2. And then we want to divide by 3 over 2, basically inverting the fraction. So we get 2 over 3, and then u to the power of 3 over 2. And all this is going to be plus c because of the constant for integration. Now we can cross these two out. We're going to get 1/3 u to the power of 3 over 2 plus c. And then if we want to go up here, we're going to get 1/3. We're just going to substitute u back in. It's basically going to be 2x plus 1 to the power of 3 over 2 plus c. So there you go. There is the derivative of that function. Again, it looks like we might not be able to apply it, but really just grab a look at the inner function. Just make sure that it's a constant function and that we can apply the substitution rule. So now to evaluate definite integrals using substitution rule, you're basically given, I'm going to give you 2 ways to evaluate them, and you choose whichever one you like. I personally like the first one, and what that consists of is basically keeping the integral as indefinite until the last step where you just apply the fundamental theorem of calculus. I think it was part 2. So here's a quick little example. Let's say you're given this integral, right? What I'm saying is keep it as indefinite. So just keep it as this, solve it as this. And it's from this solution right here, we can see that it's just going to equal to 1/3 times 2x plus 1, plus 1 to the power of 3 over 2 plus c. And only once you found this right here, the function, then you just want to apply fundamental theorem of calculus. So then you would want to go on to say, oh, okay, 1/3 times 2x plus 1 to the power of 3 over 2. We can leave out the constant because it is now definite, and then we just want to evaluate at 1 and 0. And I'm going to link a card back to the fundamental theorem of calculus. Go over it, make sure you understand it, and basically this is the first way to solve it. Now the second way to solve it is by kind of sort of changing the bounds in a sense. So if this is what we're saying, that u is equal to g of x, that like inner function, and we have this integral of f of g of x times g prime of x dx. If we have this integral, we're saying that it's basically the same thing, so it's just going to be f of u du. If you remember from the definition, it's the same thing. However, because of these bounds right here, all we have to do is, because we're kind of switching g of x, we need to apply g of x to the bounds right here. So there you go. That's all it's going to be equal to. Again, I'm not really a fan favorite of the second method. I prefer the first method, but if you like the second one, feel free to use it. So the last thing we're going to talk about is the symmetry for integrals. And if you remember from symmetry, we have 2 possible, well actually 3, the third one would be like non-symmetrical, but the 2 main ones is that it's evenly symmetrical or oddly symmetrical. So if you remember, even entails that if we plug in f of minus x, it's going to equal to f of x. And for odd, if we plug in f of minus x, well, that should equal to minus f of x. And visually, this means that we are kind of, for an even function, that we are symmetrical about the y-axis, which is here. And for oddly symmetrical, that would mean that we are symmetrical about the point of origin. So knowing these 2 things, I'm going to show you how this applies to integrals. So let's say we have this function right here, f of x, and it's even. So for the even condition, if we have an integral from a lower bound to an upper bound, and if you notice they are both a, so they're from minus a to a, well, this will just evaluate to 2 times the integral from 0 to a of f of x dx. I can show you graphically why this makes sense. So let's say we have this parabola and we're asked to find the area under the curve from -1 to 1, right? So here it is. And you could see that this area is the exact same, right? This right here is the exact same as this because it's an even function. So what we're saying is, okay, so instead of taking both of these areas, let's kind of cut this half off right here, and we're just going to find this little area and times it by 2. And again, you can see why that makes sense, because it's going to be the same area on both sides of the curve. Now for odd, let's say that f of x is odd. For odd functions, if we have the integral from minus a to a, again, it's the same bound, just negated. If we have this of f of x dx, where f of x is odd, then what we're going to have is this equaling to 0. And again, I'm going to show you graphically why this makes sense. So let's say we have this function, let's just say it's x cubed just for the sake of the video, and it's odd, right? If we're asked to find the area from 1 to minus 1 on this graph, right, we can see that these areas are the exact same area, but one is kind of under the x-axis, meaning it's going to be a negative area. So the two areas, because they're the same, they will just end up canceling each other out, and we're going to get an area of 0. That's it for the substitution rule. Essentially, it was just a way for us to manipulate the integral by substituting some function in and kind of simplifying the integral to functions that we know how to find the integral of. Hopefully this video has helped you out. Please like and comment as to what it helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.